Okay guys, in this video segment we're going to talk a little bit about carbon dating and how we use carbon dating as a way to figure out how old things are when they died. Okay, so a lot of times people think that carbon dating can be used for anything, and the reality is that's not true. So carbon dating could only be used for things that were at one point in their lives living. Okay, so if you were an archaeologist and you were to find a bone and you could pull some carbon samples out of that, you could test that. If you were to find an arrowhead made from stone, you could not test that. Okay. There are other ways to test things like arrowheads and things that are made of metals and non-carbon based things. There are other dating methods similar to carbon dating, but carbon dating is directly related to things that were living at one point in time. Okay, and the dating really only allows us to determine when it died. Okay, now in the grand scheme of thousands and thousands of years, most living organisms have a lifespan that is less than 100 years. So to know when it died is really to kind of know when it was alive, to be also. Okay, so let's kind of take a look at how it happens. So first thing we want to take a look at is how do we even get carbon-14? Because carbon-14 is an unstable isotope. Okay, its proton to neutron ratio has too many neutrons in it, so it causes a problem. Okay, the reason why it has too many neutrons in it is because one of the ways we make it is if you have cosmic radiation. Go down to this little graphic over here. If you have cosmic radiation, UV light, gamma radiation, X radiation, all this stuff comes off our sun. And as it comes into our atmosphere, okay, it actually mixes with particles up there. And one of the things that happens is it separates a neutron. Now that neutron will then go flying off, and sometimes these neutrons bombard or hit normal nitrogen in our atmosphere. Okay, we have lots of nitrogen in our atmosphere. So you have this free radical neutron that comes flying in, beams into a nitrogen, and when it does that, it causes a non-spontaneous nuclear decay reaction. Okay, so this is not one of the three common ones we talked about previously. So this is not as common because it's a non-spontaneous one. It has to happen because of energy input, which in this case, we're getting the energy from the cosmic rays. So this neutron comes in, hits this nitrogen-14, stable nitrogen-14, and what it causes a proton to be kicked out. Okay, so this is sometimes called proton emission, or sometimes also called, I believe like positive beta decay or something like that. So what happens is the proton gets kicked out. So the neutron takes the place of the proton. The proton gets booted. Well, with one less proton, we now have 6 protons, so we now are carbon. But because we added the neutron, even though we lost a proton, our mass number stays the same. So what happens is we convert from nitrogen-14 to carbon-14. Now this happens in our atmosphere all the time naturally. Okay, it's just every single day. This is just going on up there, hanging out. Once that happens, all that carbon-14 that gets created, there's not very much, but what gets created, it undergoes normal chemical reactions just like carbon-12 would. So the carbon in our upper atmosphere, one thing that happens is if you get extra carbon in our upper atmosphere, it's going to combine with oxygen in a very normal, very simple combination reaction to make carbon dioxide. This process is also natural, just happens, occurs just every day, all the time. So we have all this carbon dioxide. Well, now if we have carbon dioxide, that carbon dioxide then eventually enters our ecosystem. So now you have carbon dioxide that is carbon-14 in it in our ecosystem. Well, then that just goes into our normal ecosystem cycles in terms of being absorbed by, plants, become part of photosynthesis and all that kind of stuff. And eventually it ends up that everything in our world that was alive at one point absorbs a certain amount of carbon-14, okay? So if you're a living organism and you're breathing in air and you're eating plants and you're eating animals, or if you're a plant and you're absorbing carbon dioxide to do photosynthesis and do your thing, you're just always absorbing a certain percentage of carbon-14, okay? So as you are alive, you always have a very specific percentage of carbon-14 in your body. Okay, and then as you live and cells die off and new cells form and all that kind of stuff happens, that ratio never changes as you're alive. Okay, however, once you die, okay, when you die, you are no longer taking in new carbon. Okay, Instead, you go back into the natural process, which you start to decay, okay? And be a little bit morbid here talking about us. Let's talk about a tree, okay? So once a tree dies, it no longer absorbs carbon dioxide. It is no longer doing photosynthesis. So the carbon in its system is stagnant now, okay? So through time, the carbon is all still there. When it dies, it had a very specific ratio of carbon-14 to carbon-12. Well, 200 years pass, and the carbon-12 hasn't changed. The carbon-12 is stable, but the carbon-14 is a radioactive isotope. Okay, so what happens is the carbon-14 slowly reverses this process. So the carbon-14 slowly turns back into nitrogen-14. Okay, so over time, the carbon-14 is slowly decreasing. Carbon-12 is staying the same. Okay, so if you go in and we test a sample, let's say we test a sample of an old ship that we found, shipwrecked up in the frozen ice of Antarctica, or the frozen ice of Arctic, or down in the frozen ice of Antarctica, and we test the wood off that ship. Now, we can determine when did the tree die from that wood of the ship, which is usually pretty close to when the ship was going to be built. Okay, so the reason why we can test it is we check the ratio. So what percentage is still carbon-14? What percentage is carbon-12? And a comparison between those two ratios, because we know the half-life of carbon-14. So carbon-14's half-life is about 5,000 years. So if we can figure out that about half of the carbon-14 is gone from the sample in comparison to what should be there, it's about 5,000 years old. If it is, some other number, we can do a very simple half-life calculation, which we've already done, to determine with really good accuracy the age of that piece of wood or the age of that bone we found or anything else that we found that was able to retain its structure. Okay, so really that's how it works. It's kind of cool what happens. We have a lot of natural things going on, and then all we do is we just test the ratio between the two things, and whatever that ratio is, it tells us what percentage of the carbon-14 has decayed. Plug it back into half-life, and we know how old it is. Okay. All right, guys, that is the idea of carbon dating. Thank you.